We've now completed the basic diassembly of the core of the engine. We've done some cleaning of componentry. We just now have to disassemble the rotary valve shaft. We will then move on to inspecting the parts, checking for sizing, wear and this type of thing against the specifications. The rotary valve shaft assembly basically consists of our oil seal, bearing, a shim, a collar, the gear, spring loaded with a circlip on the top. To remove the circlip from its groove, a reasonable amount of pressure has to be exerted on the collar. A small screwdriver to be able to get in and ease the circlip out of the groove allows the collar and the circlip to come up. Spring comes off. Our drive gear. We have an O-ring and a shim. The collar at assembly time is installed with Loctite, so there will be quite sufficient force required to bring that off. I have previously disassembled this to make it slightly easier, but we'll show the sequence of removing the collar. We'll install our special tool again. Allows us to be able to impact it with the hammer. We install our protection sleeve on the end of the shaft. We will now knock the shaft, moving it to a suitable area, and we just drive on the end of the sleeve, forcing the bearing and the collar off the shaft. We now have the rotary valve shaft disassembled. We would be giving that a clean, putting it aside with the rest of the componentry ready for inspection. We've now disassembled the rotary valve shaft. We are up to checking the componentry for wear and comparing them specification wise to what's in our manual. There's not a great deal goes wrong with the rotary valve shaft. Like most of the componentry that uses an oil seal or a bearing or has a spline, there is just various areas that you need to look at. We inspect the water pump sealing area, see that there is no heavy ringing by the oil seal or marks on disassembly that may tear the seal when we put it back on. We check the spline area for condition. The sealing area on the rotary valve plate area, similarly, we are looking to see whether there's any excessive ringing. We check the end of the gear, no excessive wear. We ascertain basically that the shaft is quite okay. When we disassembled it, the bearing was nice and tight, so that would basically ensure this component's okay for renewal. As with most other oil seals, the likes of go-go type seals or O-rings, circlips, hook rings within the engine, as a matter of course we would be looking to replace those components. So we don't pay too much attention to those unless we've possibly been troubleshooting and we're looking for a reason why we may have had a leak resulting from an oil seal problem. We'll now inspect the crankcase halves for possible problems. What we are basically looking for is fretting or wear, problems associated with the bearing, ball bearing housing area. We're inspecting the sealing face of the crankcase halves, discoloration or fretting to the top, possibly from loose crankcase bolts, nicks or cuts, thread damage. These are the areas that need to be inspected. Rotary valve cover, the face area, same areas on the other half, O-ring grooves, circlip grooves, any indications. If we do not see any obvious problems here, the crankcase halves will be normally quite serviceable for reuse. I'll show you one now which is not, to give you an indication of what these actual marks look like. This is the lower half of a 503 air-cooled, which has had the magneto side bearing turning for some time. What we need to show you here is the difference between this very bright smooth surface compared to the slightly duller coloration of the area where the bearing is not located, and this resultant polished area is due to the bearing fretting, moving up and down and around in this bore. There is possibly only 0.02 of an inch wear in this area, but that's sufficient to allow excess movement of the crankshaft, resulting in oil mix leakage, contamination through the seal into the magneto housing area. We're also looking at a slight discoloration on this mating surface of the crankcase half, which is an indication of two halves moving. Alloy distracts from the bright shiny finish to this dull grey, and that is one of the indications that you look for along these type of areas where two parts are fastened together. If in any doubt about the integrity of the ball bearing housing area, if you're not certain of whether you're seeing sufficient wear that would make the item unserviceable, there is a means of being able to measure that particular area. We'll join the crankcase halves together and we'll be measuring them with a dial bore gauge. We've bolted the crankcase halves together by use of a dial bore gauge preset with our micrometer to the size of the bore area. We can now check and pick up those areas where the wear may be too far above our specification. There is actually no factory specification that I know of in this area, so I would suggest you use 0.02 of an inch as a maximum above new bore sizing. On our componentry inspection, the cylinder head, basically just check for warpage. Likewise with all the alloy componentry, excessive corrosion or damage to the sealing face areas, O-rings, threaded areas, spark plug holes in particular, ensure that they are still quite okay. Then it's okay for reuse. We're now inspecting the cylinder areas.
Dick, the cylinders can be rebored, can't they?
Yes, that's correct, Chris. The bore can be honed quite successfully or bored to two oversizers, 0.25 and 0.50 millimetre. Basically through the range of engines, two oversizers are available. Should a rebore be desired or required, they basically should be sent out to a recognised service centre. It's not something that you can undertake at home unless you happen to have the specific machinery available. We generally only look at deglazing the cylinder area to assist a new set of rings to bed in. On some occasions you can elect not to even deglaze. If the bore is quite okay in its finish, there are no deep scratches or gouges, evidence of that sort of prior problems. We measure the cylinder again with our dial bore gauge. There is specifications called up in the manual for out of round taper, and this can be quite easily found with this type of equipment. It is not the sort of equipment that you as the end user would generally have available. You can check the bore by using a new piston ring and a feeler gauge, checking the gap area. This will give you a reasonably accurate idea that of the size of the bore. However, we're using the dial bore gauge here. You just have to be a bit careful with the two-stroke because of the piston porting, that you don't get your tool caught down into the hole. We then invert the cylinder . We're showing here 0.03mm taper, which is quite acceptable. Our out of round is only 0.01mm, which is exceptionally good. Further with the cylinders, we're inspecting the O-ring sealing areas, threads, stud areas. We're also exhaust flange, inspecting to see that the cylinder sleeve has not moved within the alloy housing. We checked the port alignment, just eyeball inspection through the port, where you can see that it's lining up with the cutaway area. We now move on to the pistons. We're inspecting for size of the skirt area, condition of the piston ring grooves. Two-stroke engine, you have pegged locations in both ring groove areas to stop the ring from rotating and of course catching in a port area, resulting in a broken ring. So we'll be looking specifically at those two pegs, the ring groove areas. Piston pin area normally doesn't give us too much trouble. However, on a high hour piston there may be substantial wear there, which would render the piston unserviceable. We are basically looking at a rebuild. Our own experience indicates that we would generally be looking to replace a piston at about 600 hours. So if your piston is 300 hours or so, you are certainly looking to check the integrity of it for reuse. If you're in high hours, you wouldn't even be bothering and you'd be looking to replace it. We can check the piston ring grooves. We can carefully inspect them with a nice bright light, help show up any waviness or erosion caused by carbon between the piston ring and the piston. We use a new ring, a feeler gauge. There is specifications in the book, and it's just a case of trying the feeler gauge to see if it will go in between the piston ring and the ring groove. If it goes over the specifications in the book, it would be cause for rejection. After establishing that the ring grooves are quite okay, we use our micrometer to measure the piston skirt area. Once again, the specifications are in the book. Most measurements are taken opposite the gudgeon pin area of the skirt. They are a barrel ground piston. They are not perfectly round because of thermal expansions that happen within an engine. So we have only really two areas that we look at. The skirt area. We note the size, record it. We then come to the lower skirt area, noting the size and recording it and comparing it with our specifications. They're basically the only two areas size-wise with the micrometer that we check. We mentioned previously the locating pegs for the piston rings. We must emphasize this is a very important item to be inspected. It can be a bit difficult. However, with the aid of a small magnifying glass and a torch, you have a much better view of the area of the pin. If you get a small screwdriver holding the piston, just trying to force from side to side, ensure that the pin is nice and tight and no movement is detected. I have another example of a piston here where the pin has detached itself. The pin is missing, the hole is eroded, there is some evidence down the side of the piston that some part of the material has got caught between the piston and the bore. If we rotate the piston, we see an eroded area where the pin actually was pushed round in front of the gap of the piston ring and had been sitting there for some period of time, bouncing up and down. This eventually would have either caused galling and a piston seizure or breaking through the ringland area. It's most important that we inspect those pegs. Other areas in the piston, eyeball inspect the underside of the crown area. We do get thermal cracking occasionally in very high hour engines, or if an engine has been running with a problem. Cracks possibly up into the gudgeon pin boss area, and of course cracking on the combustion side of the piston crown. After thoroughly inspecting and measuring, we ascertain it's serviceable for reuse.
Dick, you'd expect on disassembly to find a certain amount of glaze in the cylinder bores. How do you go about honing them?
Yes, Chris, as we previously mentioned, it's been my experience that it is quite acceptable to use a spring-loaded hone to deglaze the cylinder bore. However, I might point out that it has to be a very careful exercise because the stroke is limited and you can catch the hone in the port area. We'll just demonstrate the procedure. I have a sleeve that I have made up that I can fit the cylinder into, locates it nicely and holds it firmly. As you can see, we have our lubricant or our cleaning solution, our dieseline kerosene mix, which helps the hone. What we firstly must ascertain is how much stroke we can use on the hone. We insert the hone into the bore, lightly taking the tension, noting where it comes out on the bottom of the cylinder and noting the depth of the collar, and this will be our limiting depth. We insert the hone in the driving collar, ensure that the assembly is quite okay and working. Reinstall the hone in the bore. Take up our tension. We just want a light deglaze. Normally 30 seconds or so is quite enough. So we are now carefully in position. We have the collar and the hone in an area where it is not going to catch in a port. We just need nice even strokes up and down. The drill is slow revving and we'll get a nice even finish. Making sure that we are moving up and down all the time, and if we do stop, we take the collar off and release the tension without pulling the hone straight up the bore. We will be washing the surface area, cleaning it sufficiently to allow us to see exactly how much honing we've done and if we have sufficient removed. This being the case, we would then wash the cylinder in a fresh solution of petrol or cleaning material, kerosene. It is then hosed off or blown dry, sprayed with some WD-40 dewatering type fluid, and then I must emphasise that it is to be again washed in a household detergent type solution, or I use Amway Industrial Clean detergent, wiped with a rag, blown dry, and then re-oiled and wiped again with a rag to remove any possibility of grit being embedded into the cylinder area. This will still leave a slight coating of oil, and the cylinder could be left just under cover of a nice clean cloth whilst we're assessing the parts and in preparation for the assembly, with no deterioration or rusting occurring. We're now looking at the crankshaft area, our final disassembly prior to assessing our parts requirements. Generally at 600 hours I would recommend, and it's been my experience, that you would need to replace the outer crankshaft ball bearings. There is tools available, like the other special tools that are required. However, for the one-off aircraft owner, they would not generally be used, and you would probably be wiser to send the crankshaft and any other items that can only be serviced by a distributor or a service centre into those areas to be repaired. However, we will show you the removal and replacement of the outer bearings. The crankshaft in construction is a press fit. The components can be replaced. Conrod kits are available, however they are only available and serviced through distributors. We will not be looking at any of that area, only just removal and replacement of these bearings. We're now removing the bearings. We put our spacer collar, we are pulling the top bearing off first. Our split ring halves installed. Our retaining ring. We have our protection mushroom protecting the end of the shaft. Our puller assembly located over. Puller bolts are screwed in, their full depth. The construction of this puller is such that we need to hold the outside area and screw the centre bolt. Once the bearing has started to dislodge, we can then switch to a ratchet, and it also helps to turn both tools together. Rotating the bearing makes it easier to remove it from the shaft. Keep rotating the bolt until the bearing comes free. Withdraw the puller with the bearing from the shaft. Disassemble the tool. We remove the spacer ring. Fit our two ring halves again. The outer ring. Insert the puller. winding our bolts down. Taking up the tension, removal procedure is identical to the outer bearing. Moving both assemblies. And the bearing is easing its way up the shaft. Working the tools around until the bearing releases and comes off the shaft. The bearings we've removed here are from the PTO end of the crankshaft. The magneto end on the various models only uses one particular bearing on that end. Removal procedures are exactly as we've shown. Refer to the maintenance manual for the appropriate tool part numbers. We would basically be looking for inspection to see whether the bearings had possibly been turning. You can get an indication by using the puller if a bearing is tight or if it's loose. We're looking for severe wear that may have allowed the bearing to be actually turning on the shaft and fretting or eroding this particular area. In this instance, it's quite good. There was a fair amount of exertion required to remove the bearings from the shaft. We would be looking at just putting new bearings on this shaft. With the installation now of the bearings, we will remove the crankshaft from the vise. As we'll be tapping the bearings on, we now just insert, I have a piece of spring steel here, slightly cut out, which goes underneath the web and will support it, so we don't put any undue stress on the pressed parts of the crankshaft. It's just sitting located in the vise, just slightly nip it up so it doesn't move about. With this particular installation, we do have a 2mm spacer which will limit where the bearing, the bottom bearing goes. We will be knocking this bearing on with a hammer. There's a bit of jarring. We just put a little bit of tape around to stop the tool coming off whilst we're doing that. The bearings do require to be heated 60 to 80 degrees Celsius. We do this via a heat gun. This just makes installation on the shaft that much easier. The bearing also is to be installed with the back side of this cage towards the crank blade. We have a sleeve and a tool made up that we can locate on the end of the bearing to tap it on. We generally just feel the bearing if it's rather warm to touch. You don't need to overly heat them. We set the bearing on the end. Quickly putting our drift on. Okay. The outer bearing is again spaced out. We have these two halves which are installed above the bearing we've just put on. Again, we put a slight amount of tape around, and again we preheat the outer bearing. With our bearing now at the right temperature, the bearing is installed in reverse to the inner bearing, we now have the back side of the cage facing outwards. Using our same tool, we just again take it down until it lightly makes contact with the spaces and leave it at that. We can then remove our tape, remove our spacers, that leaves our bearings in our correct alignment. We would then remove the shaft from the vise as we have it mounted here, ensuring that you have alloy jaws so there is no damage to the bottom part of the shaft. We would then oil those bearings and just ensure that we have not got any possibility of small bits of aluminum from the drift or this type of thing. We're now up to the assembly of the rotary valve shaft assembly. We have already assessed what parts are required. We would always renew the oil seal and the O-rings circlip as previously mentioned. Prior to installing anything on the shaft, we give a good degrease and a cleaning with a Loctite primer T-type substance. A small amount of a silicone lubricant just to help ease the sealing lip of the oil seal over the shaft. The bearing is installed over the shaft, will now be driven on. Just a punch and a tube. Bearing is hammered down until it stops against the collar. Prior to installing the collar, we will again degrease and clean that area. We have to apply some Loctite 680 on this area, so we don't want any of the silicone lubricant remaining. We put on our shim. All this is laid out in the manual, shows you exactly where things go. We apply a liberal amount of the 680 over the shaft, sliding the collar on, slight bit of a workaround to spread the Loctite. We would then be heating this up to about 60 or 70 degrees with a heat gun. This helps the Loctite harden and we can carry on with the assembly. Okay, we've warmed our collar up, we've set the Loctite off, we carry on with the assembly. We have a shim and our new O-ring, our drive gear. We're fitting the spring, the collar and our new circlip. We're pressing down with our thumbnails on the circlip whilst we're pressing down and loading the spring until the circlip clicks into its groove, leaving us with the assembly complete. The gear must be able to move on the spring. Right, we've assembled the rotary valve shaft. We're now looking to assemble this into the crankcase. Prior to that, we've previously removed the bearing from the water pump housing area. We now have to refit that bearing. We would be putting a new one in. This bearing can only be replaced when the crankcase halves are disassembled at rebuild time. It has to be installed through the rotary valve area, slid along until it locates in the bore. We use a sleeve and a drift to lightly tap it in. Until it locates itself against the boss. We might just make note here, on the later engines, they now put a circlip in there to retain that bearing. Engines that have only just come out in the last 3 months. We now move on to installing the rotary valve shaft assembly, remembering to first preheat the crankcase bearing area. We install it through from the actual rotary valve side. There is a special tool required for this. The end of the shaft will contact on here. This will also locate the seal area, and it is just a case of drifting the bearing in. The shaft is drifted in until it comes up against the shoulder. Ensure that the movement feels correct, the bearing is not impeded in its movement. We'll now be installing the circlip from the rotary valve plate end. Right, now we're up to assembling the crankshaft to the crankcase area. We've basically finished our cleaning, but there is just an initial process we use prior to fitting the crankshaft into the crankcase. We need to ensure that the mating face area is completely free of any oils or possibly some of the old 515 that might still be on there. We give it a light spray over, wiping it off. This particular product is also a primer, which initially will make our sealant go off a bit quicker. We don't particularly want that in this instance when we're assembling the crankcase halves, so we're basically only using it for cleaning purposes. We also put some more on the inside of the bearing area. Our crankcase halves now are ready. We just have to put our new O-rings and our seals on our crankshaft prior to installing it in the crankcase. There is some differences between the various engine models as far as the crankshaft O-rings go. Once again, it's a case of referring to the applicable section in the manual. The O-rings are just worked over and go into the outside groove area of the bearing. These are used to assist in retaining the bearing or stopping the bearing from rotation whilst the engine is extremely warm or operating at its maximum temperature, and or on the initial startup the engine is very cold. So we put the O-rings on the bearings. We then install the seals. Prior to this, we just put a small amount of silicone lubricant around the inner lip of the seal area. We install the seal on the end of the shaft, pushing it right up to its mating surface on the outside of the bearing. Prior to installing the crankshaft, we'll just pre-lube the seals and a bit to the centre bearing areas. On installation of the new outer bearings, we have already put some lubrication around them. Small amount down around the connecting rod bearing, even though this can be done later. We will then be installing the crankshaft, making sure that the locating rings match the centre area, the O-rings into their respective slots, and the seals hard up against the end of the bearings. We would then be applying our Loctite 515 master gasket to the sealing faces, just a light amount, just enough to get sufficient coverage. We do not want excess of this sealant. It's only necessary to apply it to one surface, just working it in, nice even coverage with your finger. When we have a nice even coverage, all the surface area has a light coat,